Can energy conservation be used to predict the behavior of a system? This is the question students explore in Investigation 10C, Springs and the Conservation of Energy. This investigation has 3 parts. In part 1, students use energy conservation principles to predict how far a cart attached to a spring will roll down a track inclined at 30 degrees. In part 2, students measure the spring constant of their spring in preparation for their prediction. And in part 3, students calculate their prediction and then test it using an actual cart and spring system. In part 1, students derive an expression that predicts the maximum distance the cart rolls down the track after being released from rest at the top. Top is where the spring is unstretched. At the top, the system has only gravitational potential energy. If we assume that height is 0 at the bottom, the system has only spring potential energy at the bottom. Using conservation of energy principles, the energy at the top is equal to the energy at the bottom, which gives this expression. Using that expression, students can solve for the distance down the track x in terms of the cart's mass, the spring constant k, and Earth's gravitational acceleration g. Students should recognize that if the track angle is 30 degrees, the vertical height that the cart travels is equal to x over 2, which helps simplify their expression. Before students can calculate their prediction, they must measure the spring constant of their spring. Students do this in part 2. Attach the feet and end stop to the track, and then make sure the track is level. Mount the hook to the front of the smart cart. Open the 10C spring constant experiment file and connect the cart using Bluetooth. Once the cart's connected, zero the cart's force sensor while nothing is touching the hook. Connect the spring between the top of the end stop and the hook on the front of the cart. Then, adjust the position of the cart so the spring is just about to be under tension. Begin recording data and then slowly pull the cart about 70 centimeters down the track. Data recording stops automatically after 4 seconds. In the software, highlight the straight portion of the data and then activate a linear fit. The slope of that linear fit is equal to the spring constant. In part 3, students calculate their prediction and then test it using this cart and spring system. Attach the track feet, end stop, and angle indicator to the track, and then mount the track to the tripod using the track bracket such that the incline angle is exactly 30 degrees. Attach the stiff spring between the top of the end stop and the hook on the front of the smart cart. Place 2 cart masses in the top of the cart. Open the 10C Energy Transformations experiment file and then reconnect the cart using Bluetooth. Hold the cart on the track so that the spring is unstretched. Start data collection, release the cart, and then catch the cart at the top of its rebound. Data collection stops automatically after 3 seconds. Use the statistics tool in the graph to determine the maximum distance the cart traveled, and then compare that value to the predicted value. Students also use their data to complete the table in the handout and then calculate values for the system's total energy at the top, the bottom, and the middle of the cart's travel. Using those values, students calculate the efficiency of the energy conversions throughout the system.